This meeting is being recorded.
So our speaker today is Luis Felipe Garcia, and his title, you can see there, is Operator Algebras over P-adic Integers. Please, Luis, go ahead.
Okay, so first I want to thank Professor Gisela and Professor Cortines for the invitation. So this is joint work with Alcides Bus and with Devarshi, who is here. And okay, so we are going to talk about operator algebras over the p-adic integers. Right. So let's start with some motivation. So the starting motivation for this project are the Kaplanski idempotent conjectures. The Kaplanski conjecture states that for any ring R and for a torsion-free group G, the group algebra RG contains no non-trivial idempotents. So in the complex case, this is known for a very large class of groups. And to prove these results, it used some techniques from system algebras. So the main motivation to introduce this p-adic system algebras is to try to solve the Kaplanski conjectures over Fp, the field with p elements, and over Zp, the p-adic integers. And I also have a secret motivation that I always wanted to see if it's possible to develop a theory of operator algebras over a general Banach ring, say. So this is my secret motivation. Okay, so what is the idea? Let's quickly recall what a system algebra is. So we can define a system algebra to be a Banach style algebra that can be isometrically represented inside a space of bound operators on a Hilbert space. And this definition encompasses both the complex and the real system algebras. So the idea to define a p-adic system algebra would be to copy this definition right here for p-adic algebras. So Professor Andreas Thom and his PhD students, Anton Klausnitzer, have introduced the notion of p-adic Hilbert space. So these p-adic Hilbert spaces are a certain kind of topological module over the p-adic integers that share some interesting properties with the usual Hilbert spaces. They have self-duality and they have a version of the His representation theorem, right? Oh, so if you want to ask any questions, you can pause me anywhere, okay? So right, so Andreas Stone and his PhD students has this notion of p-adic Hilbert space. And our idea to define a p-adic version of a system algebra is to set it as a Banach style algebra of Zp that can be isometrically represented inside this p-adic Hilbert space. But working with this definition of p-adic Hilbert space is a bit challenging because it has a topology that is kind of hard to deal with. But after some talks with Professor Hofmeier, we have managed to show that we can use these C0 spaces instead to represent our algebras, and we have the same category at the end, right? And it is this theory that we are going to present today, right? So let's recall what the p-adic numbers are, okay? So starting fixing a prime p, and for a non-zero integer a, let VPA be the number of times p divides a. So for example, V2 of 4 is 2 because 2 divides 4 2 times. And V3 of 6 is 1 because 3 divides 6 1 time. And also set VP of 0 to be infinity, right? This function VP is called the p-adic valuation, and it can be used to define a metric on Q, the rational numbers, via this function right here. So we take a norm of a fraction a over b is p to the power of vpb minus vpa, right? This function is called the p-adic norm and satisfies these three properties right here. So the p-adic norm of rational number x is 0 if and only if the number is 0. The norm is multiplicative. And then p-adic norm of a sum is less or equal than the maximum of the norm of each term, right? For each rational number, x and y. So this third expression right here is called the ultrametric inequality, and is actually stronger than the triangle inequality. With this inequality right here, we can easily prove the triangle inequality, right? So we define QP, the p-adic numbers, to be the completion of Q with respect to the p-adic norm. And this is a complete normed field, right? And the p-adic numbers are similar to R, the real numbers, in the sense that they are both completions of the rational numbers, right? And Ostrowski theorem states that there are only two reasonable ways to complete the rational numbers to get a complete norm field, the p-adic numbers and the real numbers, right? But the algebraic and topological properties of the p-adic numbers and the real numbers are drastically different. For example, QP as a topological space is totally disconnected, right? Okay, so we define the p-adic integers to be the p-adic numbers that has norm less or equal than 1. And this is a closed subring of QP. This is a subring thanks to the ultrametric inequality, right? And the p-adic integers are a principal ideal domain, right? With only one maximal ideal, PZP. And the ring of integers, the usual ring of integers, can be seen as a dense subring of ZP. Okay? So now let's talk about DC zero spaces. DC zero spaces is where we are going to represent our algebras on. So starting fixing a set X, an arbitrary set, and define C0 XZP to be the space of functions X to ZP such that it goes to 0 at infinity. To go to 0, it means that for every epsilon bigger than 0, there exists a finite set f of x such that everyone outside of the set f has norm less or equal less than epsilon, right? So this space right here, C0 XZP, with the subnorm becomes a Banach ZP module, meaning that it is a complete metric space and it's a module with continuous operations, right? And on C0 XZP, we can define a pairing, a bilinear, a continuous symmetric non-degenerate bilinear form. To do this, we take two functions, xi and eta on C0, and define this pairing right here. We take the sum over the products of every value of the function. And this sum is well defined because a function on C0 XZP has countable support, right? So this function is a countable sum, and to converge over ZP is a lot easier than to converge over the real numbers or over the complex numbers. So this pairing is well defined, is continuous, symmetric, non-degenerate, and we are going to call it the canonical pairing, right? Now that we have a canonical pairing, we can define what it means to be adjointable with respect to this pairing. So a boundary operator T on C0 XZP is said to be adjointable if there exists another boundary operator S such that this adjointability condition right here holds, right? So as the canonical pairing is non-degenerate, this operator S is unique if it exists. And we are going to call it T star, right? So we have a notion of adjointability in this setting, right? So we can define BC0 XCP to be the star algebra of adjointable boundary operators on C0 XCP. And with this operator norm here, we are going to define the operator norm in the same way that is done over real functional analysis and over complex functional analysis, right? And we have this space of boundary operators on C0 XCP. And when X is a finite set, this space BC0 XCP can be naturally identified with the space of n by n matrices with transposition as involution. So the adjoint operation, the star operation, is like the transposition in this setting. right? So finally, we can define what a p-adic operator algebra is. So for us, a p-adic operator algebra is a Banach ZP algebra together with an evolution, turning it to a Banach style algebra that can be isometrically represented inside a space of boundary operators on C0 x ZP. And for us, a morphism of p-adic operator algebras is a contracting star homomorphism. So this is another difference from the theory of system algebra, is that our morphisms are not automatically contractive. We have to ask to be contractive, right? So this way we have a category of algebra P, the category of p-adic operator algebras.
Sorry, may I bother you? Didn't my recollection in your paper, you didn't have C0x that
Yeah,
but something with the QP and
yeah. This QPX was
yeah.
the Antonin Clausewitz notion of p-adic Hilbert spaces.
Uh-huh.
But after talking with Professor Half, we managed to show that these two notions of p-adic operator algebras, they are the same.
Oh,
Every
really? Mhm.
yeah,
Oh, I mean, I should say that they give the same, like, they give the same B of that thing. They're not the same as uh,
Yeah, the
topological model.
space. But they give the same B. How
Yeah.
it's
yeah, yeah. The boundary operators are the same. Yeah, yeah. Okay.
okay.
Right. So let's start with this first example. So start fixing a topological space X and consider the algebra of continuous functions CXZP with trivial evolution. And we can represent this algebra CXZP inside BC0XZP as follows. So we take a function f and send it to this representation M does the following, does this following right here, right? So this way we can isometrically represent CXZP, right? And note that we have not to ask to be bounded functions because ZP has norm at maximum 1. So all continuous functions are automatically bounded, right? Right, and we also have group algebras. So for any group G, we can equip C0GZP with a convolution product given by these formulas right here. So these are the usual formulas, right? For those that work with system algebras, Steinberg algebras, this must be very, very familiar. And we can represent it via this left regular representation. We represent C0GZP on C0GZP itself via this left regular representation, right? Okay, another example is an example for number theory, from number theory, the Tate algebra. Define the Tate algebra to be the ZP algebra of the ZP subalgebra of the ring of formal power series ZPT, made of formal power series such that the coefficients goes to 0 as the index row. So this is the Tate algebra right here. So formal series such that the coefficients goes to 0 as the index row. And consider this algebra with the trivial evolution. So ZPT, the Tate algebra, is a p-adic operator algebra.
I mean, I should say that this is not what is called the Tate algebra. This is just the algebra of convergent power series. It would be quotients of these that would
Oh,
be
okay.
called Tate algebras. And
Okay.
also there's
No,
generic fiber. Yeah.
Yeah.
But
So a Tate algebra.
this is the free one
Yeah, the free
in
Tate
one
algebra.
variable.
Yeah, yeah.
and the integral one.
Okay.
Yeah.
Okay. Right. So this is a p-adic operator algebra. We can represent it. It's a little bit harder to represent it than the group algebra and the continuous algebra of continuous functions. but we can represent it. There is this a split representation, right? And now let's talk about another example, the Gaussian p-adic integers. How does this work? So starting fixing a prime p such that this equation right here, x squared plus 1 equals 0, does not have a solution in ZP. So over ZP, sometimes these polynomial equations has a solution and sometimes it don't, depending on the prime p. So choose a prime p such that it does not have a solution, right? So we can formally add a solution by considering this algebraic quotient right here. So we formally add a solution and call it the solution I. And every element of ZPI can be uniquely represented as a plus BI with A and B in ZP. And we can define a norm on ZPI to turn it into a Banach algebra and a star operation, right? We define a norm of A plus BI to be the maximum of A and the norm of A and the norm of P, and define the evolution just like the complex conjugation, right? And ZPI is a p-adic operator algebra. And we have this isometric representation right here. We take a sum A plus BI and set it to the matrix A minus B, BA. Very similar to the complex representation over M2R, right? Right, and we have this problematic example. So we have this another example, the TP2 algebra. So consider this algebra, TP2, made of square 2 by 2 matrices, strictly triangular 2 by 2 matrices with coefficients in ZP, with trivial evolution. This is a commutative algebra, and if we take any two elements of TP2 and we multiply them, we get 0. So this algebra right here has a trivial multiplication, right? And we can actually represent it. So let's represent in the case that P is a prime number such that this equation has a solution. This time we are asking to this equation to have a solution and call the solution I, right? We can represent it this way. We take a square 2 by 2 matrix of this form and send it to A times this matrix right here. This matrix does the job because it's self-adjoint matrix. It's a symmetric matrix, and its square is 0. So this is an isometric representation of TP2. And this example teaches us the following, that the Gelfand theorem does not hold in this setting. Notice that TP2 is a commutative algebra, but it cannot be of the form of an algebra of continuous functions. Because TP2 has an element such that it's non-zero, but its square is 0. And no algebra of continuous functions has an element which is non-zero and with square 0, right? And TP2 also does not satisfy the C-star identity. So in general, the p-adic operator algebras do not satisfy the C-star identity, right?
Excuse me. Sorry, just a question. Like why, in the case of the complex numbers, why wouldn't the previous representation be
Yeah,
work as an isometric isomorphism? I know that it doesn't work, but I'm just curious why.
yeah, because this right here, the adjoint in this setting is the transpose, but the adjoint over the complex numbers is
Oh,
the
yeah.
Hermitian, right? The complex
Yeah.
conjugate.
Of
So,
course. Yeah, makes
so
sense.
yeah, this is the difference.
Okay, thank you.
Yeah. Okay, so now we also have a tau groupoid algebra. So given a G and a tau groupoid, and one can define a p-adic operator algebra of an tau groupoid in a very similar manner that's done over the theory of system algebras and the theory of Steinberg algebras, right? Very similar. Okay, and we also have direct graphs. So it is well known that we can attach to a direct graph an étale groupoid via the Renault-Diacono construction, right? And this groupoid GE, say GE, the Renault-Diacono groupoid, is a locally compact Hausdorff and totally disconnected groupoid. In other words, it's an ample Hausdorff groupoid. And we define the p-adic operator algebra of the graph E to be OPGE, right? But not every Banach algebra of ZP is a p-adic operator algebra. There are some restrictions. The algebras must be torsion-free, right? Every p-adic operator algebra is torsion-free, and the norm must only attain values where the norm of ZP attains values. So, for example, FP is not torsion-free, so it cannot be a p-adic operator algebra. And, for example, QP is also not a p-adic operator algebra because its norm does not attain values where ZP attains values. For example, it has an element, say 1 over P, that has norm bigger than 1, right? And also we have examples such as we take CP, we take the p-adic numbers, we take the algebraic closure, and then take the completion again. Then we have this algebra CP, which is algebraic closed and complete, and contains the p-adic numbers. And we can take, for example, the unit ball of CP. This is also not a p-adic operator algebra, because its norm attains values where ZP does not attain values, right?
But sorry, but these look like very weak
Yeah,
restrictions.
very weak.
I mean, the first guess would be that that there should be more, but that's just a wild guess.
Yeah. But we still don't know if there are more restrictions than that. We still don't know. We suspect, at least I suspect, that these might be the only restrictions, right? And we are going to see why in very soon. Okay? So now let's talk some categorical properties of the p-adic operator algebras. So first property is that it has all limits. So in particular, we have products, pullbacks, and equalizers, right? So we can do these constructions. And we have an enveloping functor. We have a universal p-adic operator algebras. Let's see how this is done. So start fixing a star algebra of ZP, right? Just a star algebra without any norm. There exists a p-adic operator algebra AU, which is universal in the following sense. There is a star homomorphism from A to AU with dense range, such that for every p-adic operator algebra B and every star homomorphism from A to B, there exists a unique p-adic operator algebra phi from AU to B, that commutes the triangle. In other words, we have we have a functor from star algebras over ZP to the category of p-adic operator algebras that is left adjoint to the forgetful functor, right? But this functor, this enveloping functor, might destroy some information. For example, FP is a star algebra of ZP, but its enveloping is 0. So the enveloping functor might destroy some information, right? And now let's talk about the canonical p-adic norm. So along every norm, there exists some norms that are special in such a sense. A norm ZP module M is said to have a canonical p-adic norm if an element has norm less than 1, if and only if it's divisible by P, right? So this is so for example, group algebras and the algebras of continuous functions and the Tate algebra we just saw, they all have the canonical p-adic norm, right? And a counter example for this would be PZP, the principal ideal PZP of ZP, on PZP, the element P is not divisible by P because 1 is not an element of PZP, right? So P in PZP has norm less than 1, but is not divisible by P. So we have these pathological examples right here, right? Okay. And we have a result about this canonical p-adic norm that if A is a star subalgebra of BC0XCP such that its induced norm is the canonical p-adic norm, then the developing algebra AU is isomorphic to A hat, the house of completions with respect to the canonical p-adic norm, right? So this is very good because we explicitly know who developing algebra is. So a problem of this developing functor is because often it's very hard to know who developing algebra is. But in this case, when A carries the canonical p-adic norm, we explicitly know who developing functor is, who developing algebra is. Right. So another example where we explicitly know who developing algebra is the following. So when G is an ample house of groupoid, we can consider its p-adic operator algebra, and we can consider the Steinberg algebra of G, right? In this case, we have the developing algebra of SPG, the developing algebra of the Steinberg algebra of G is the p-adic operator algebra of the groupoid. So this is another example where we explicitly know who developing algebra is. Right. Okay. So with this information, we can talk about the direct graphs. So recall that when R is a commutative unitary ring and E is a direct graph, recall that the Leavi path algebra LRE is isomorphic to the Steinberg algebra of G, the Renaud-Diacono groupoid. And as we had the previous results, that SPG U is the p-adic operator algebra, we have that OPE, the p-adic operator algebra of the graph, is the universal p-adic operator algebra generated by pairwise orthogonal projections V for each vertex V, and partial isometry Z for each edge E, satisfying the usual relations right here, right? So this is the p-adic operator algebra of a graph. So a special example of this is are the Kuntz algebra, right? So let En be the graph with a single vertex and n loops. We can define the p-adic Kuntz algebra to be OPN. And this is the universal p-adic operator algebra generated by n isometries, S1, S2 to Sn, satisfying the usual Kuntz relations, right? Okay. So another categorical property is that p-adic operator algebra has all colimits. So in particular, we have coproducts, push-outs, and co-equalizers, right? Okay. And with all these good categorical properties, it's very easy to build new p-adic operator algebras from old ones, right? Okay, so now let's talk about tensor products. The category of p-adic operator algebras admits at least two natural tensor products, a maximal tensor product and a spatial tensor product, very similar to the category of sister algebras. So first, let's talk about the maximal tensor products, how the maximal tensor products works. We take two p-adic operator algebras, A and B. The maximal tensor product is, first, we take the algebraic tensor products, and then take the enveloping. This is the maximal tensor products, right? So the maximal tensor products satisfies a very interesting universal property. So given three p-adic operator algebras, A, B, and C, and two morphisms, phi from A to C and B to and C from B to C, let these two morphisms be two star morphisms such that they commute in the images, right? In this case, there exists a unique morphism P from the maximum tensor product to C that satisfies this equation right here, right? And we have this property right here that if A and B are unital, star algebras of ZP, we have that the maximal tensor products of the developing algebras is isomorphic to developing algebra of the algebraic tensor products. Okay, so now let's talk about the spatial tensor products. So first, formally define the tensor C0xZP, tensor C0yZP to be C0x times yZP. And given two functions C and eta on C0xZP and C0yZP, define the tensor products to be, we define the tensor of C tensor eta on xy to be Cx eta y for every x in x and y in y, right? And given two operators, u in BC0 xZP and v on BC0 yZP, define the tensor products on this operator, define on these elementary functions right here, we are to be this. So this delta x function is the function that at x values 1 and 0 otherwise. So this completely defines the operator u tensor v, right? And we are going to define the spatial tensor products as follows. So given two p-adic operator algebras A and B represented by pi and sigma, respectively, define the spatial tensor product to be the completion of the ZP algebra generated by these tensors right here inside BC0x ZP, tensor BC0y ZP within this norm. So this is the spatial tensor products. Okay. And we have a theorem relating the maximal tensor products and spatial tensor products when the algebras have the canonical p-adic norm. So if A and B have the canonical p-adic norm and such that its induced norm on the algebraic tensor product viewed inside BC0 x times yZP has the canonical p-adic norm, then the maximum tensor product and the spatial tensor products coincide. So this is a very nice result, right? So in particular, we have this corollary that the maximal tensor products and the spatial tensor products of the space of boundary operators coincide. Okay, so another example where the maximal tensor product and the spatial tensor product coincide is the following. So let G and H be ample Hausdorff groupoids. The maximum tensor products and the spatial tensor products of the p-adic operator algebras coincide, and they are both isomorphic to the p-adic operator algebra of the direct product of G and H. Okay? And now let's talk about the O2 stability problem. Recall that for complex Kunz algebras, O2 and O infinity, recall that O infinity is the Kunz algebra with countable infinity many generators, and O2 and O infinity have the self-absorption property, meaning that O2 tensor O2 is isomorphic to O2, and O infinity tensor O infinity is isomorphic to O infinity, right? So we have managed to show that p-adic Kunz algebras do not satisfy this self-absorption property, meaning that for every prime p, the p-adic Kunz algebras have the property that OP2, tensor OP2, is not isomorphic to OP2, and OP infinity, tensor OP infinity, is not isomorphic to OP infinity. So this is a consequence from the fact that the Leavi path algebras over the field with p elements do not satisfy the Kunz absorption property, right? The self-absorption property. So this is a consequence of this fact. And the tensor right here can be both the maximal and the spatial tensor products. Right. So another construction that we can carry from the Archimedean world is the cross products. So just like the tensor products, there are two reasonable ways to construct them. One is very explicit, and the other one is indirect, using the enveloping functor, right? But we are going to see that in good cases, these two constructions coincide. So first, the reduced cross product. So let A be a p-adic algebra and G be a group acting on A via an action alpha. We can construct the reduced cross product as a module to be C0GA, that is functions from G to A that goes to 0 at infinity. And we're going to define convolution and involution just like the usual algebraic case. So these formulas must be very familiar for those that work with system algebras. So these reduced cross products we can explicitly represent. So there exists an explicit representation. And the other construction is the maximal cross product. So first, we define the algebraic cross products, okay? Rather than working with C0GA, we work with CC, that is functions from G to A with finite support, with the usual convolution and involution formulas, right? And the maximal cross products is the following. So given an action alpha from G to A of a discrete group, the maximal cross product, first we take the algebraic cross products of alpha, and then take the enveloping. This is the maximal cross product. Right. So we have a theorem. When A is unitary, this unitary condition is actually important, right? When A is a unitary p-adic operator algebra and alpha an action of G in A, there exists an induced action alpha U on the enveloping. Okay? And we have this isomorphism right here. So the maximum cross product of alpha is isomorphic to the maximum cross product of alpha U, the induced action, which is isomorphic to the reduced cross products of alpha U. We have this result right here, right? A corollary of this fact is that if A is a unitary p-adic operator algebra, with the enveloping being equal to itself, then for every action alpha, the maximal cross products and the reduced cross products coincide. Very nice results. But recall that we have this unitary condition right here. But when A carries the canonical p-adic norm, we can drop the unitary condition. So if A is a p-adic operator algebra that carries the canonical p-adic norm, then the maximum cross products and the reduced cross products coincide. Right. So another result, let's recall the action groupoid. Recall that when X is a locally compact Hausdorff space and H is a group acting on X, recall that we can build a locally compact Hausdorff étale groupoid, X cross H, the action groupoid, right? And we have a result about this action groupoid, which is the following. So again, let X be a locally compact Hausdorff topological space and H a group acting on X. The action A induces an action alpha of H on CC XCP via this dual action right here. And there is a canonical isomorphism. The cross products of alpha, the maximum cross products, is isomorphic to the reduced cross product of alpha, which is isomorphic to the p-adic operator algebra of the action groupoid X cross H. So this is a very nice result. Okay. Okay, so now let's head to the final part of the presentation. Let's talk about the GNS theorem. So we already know that the p-adic operator algebras do not satisfy the Gelfand theorem, meaning that algebras of continuous functions are not, in general, algebras of continuous functions. Not every commutative algebra is an algebra of continuous functions. But we still don't know if some sort of GNS holds in our theory, right? Our best attempt consists in expanding the range of bilinear forms. So if we add...
But do we know that, do we know anything about the general structure of a commutative p-adic operator algebra?
Yeah, we still don't know. We still don't know.
Yeah,
Right?
no, I mean, what I was wondering was what you meant when you said that we know that we don't have Gelfand-Naimark theorem.
Yeah,
He,
no,
he meant that not every algebra is continuous functions.
yeah,
Not every commutative one is continuous functions. For example, the Tate algebras.
yeah, exactly.
Hmm.
Recall the example TP2. TP2 is not an algebra of continuous functions.
Okay.
So this is what I meant, right? But we still don't have a structure for commutative algebras. But maybe there is some sort of theorem uh, uh,
Some
explaining who.
characterization. There
But
might
the
be
Tate
some
algebra
characterization.
is
Ah,
the Tate algebra is a ring of like analytic functions on the closed disk. So
Oh,
there could still, I mean, I guess what I'm trying to say is that we don't know if continuous functions is the thing we're looking for, but some other
yeah, maybe,
like
maybe.
analytic functions or something of that
Yeah,
sort.
yeah, yeah. But yeah, yeah. I was just saying like explicitly C0 of someone. C of topological space, just as usual, right? Like TP2 cannot be an algebra of continuous functions, but maybe with some sort of different notion of uh, continuous functions. Yeah. Okay. But notice that until now, we just consider on C0 XCP the canonical pairing. But if we add every non-degenerate continuous symmetric bilinear form, then every Banach algebra that is torsion-free and such that its norm only attains values where the knob of CP attains values, then we can represent every such algebra on BC0 XCP if we add every non-degenerate continuous symmetric bilinear form, right? And to prove this result, we are going to prove this result not over ZP, but we are going to prove this result over complete non-Archimedean fields, right? This is because this is algebras over fields behave much, much better, right? And we avoid pathological examples such as PZP. But I think it's possible to prove this result just with CP, right? Okay.
Sorry, just something. On the previous page, what does it mean to like add every non-degenerate continuous symmetric bilinear form? I didn't understand what the like what you meant by this
Uh,
directly. Like,
Yeah, on C0XDP, recall that we are considering an explicitly, uh, let me, let me go here. Recall that on C0XDP, we are considering just one canonical pairing. The pairing that takes two functions C and eta and takes the sum of the product of each term.
mm-hmm.
But there are another non-degenerate pairings, right?
Oh, okay.
Okay, so there's this other pairings, different pairings.
Yeah. Okay.
Yeah.
Thank you.
Okay, right. So we are going to replace ZP with a complete non-Archimedean field. A complete non-Archimedean field is just a complete normed field that satisfies the ultrametric inequality, right? Right. Let's prove this result. So starting fixing K a complete non-Archimedean field, and define a pseudo-Hilbert space over this K as a Banach vector space H, such that its norm only attains values where K attains values, with a non-degenerate symmetric bilinear form that satisfies this relation right here. So the sup over eta with norm less than 1 recovers the norm of C, right? There exists a result of non-Archimedean functional analysis that says that every Banach vector space over K, such that V only attains values where K attains values, is isometrically isomorphic to C0 xk. So every pseudo-Hilbert space is of the form of C0 xk for some set
I
X.
think you need the field to be discretely valued for this.
Uh, uh,
But yeah, for QP, this is true.
for QP, it's true. Okay, okay. I'm not sure if this is true, but okay. Let's define what a state is. So for us, a state in a unit of star-Banach algebra A is a continuous linear functional from A to K, satisfying that it is symmetric and such that its norm is equal to 1. Okay? So define a quasi-system algebra over K to be a unit of Banach star algebra such that its norm only at these values or K at these values, satisfying this system property right here. The system property is the following. It's a bit weirder than the usual system property. Is that for every element A in A, there must be a state phi such that this sup attains the value of A. The sup is over every B and C in A with none less than 1.
Uh,
This,
What's your definition of state?
the
Just an
definition of
element of
state
the dual, or I forgot.
is this.
Okay.
Okay?
Okay.
It's a symmetric. Okay?
Okay.
So notice that this formula right here, with each state, we are going to define a pairing, right? Notice the similarity of this formula right here and this condition right here, right? So each state will define a pairing, and we are going to proceed just as the usual GNS. Each state will define a pairing. Each state will define a pseudo-Hilbert space and a representation. And then we are going to sum up every such state. So this is why we have this property right here. The property says that there exists such a phi for every A. So with this property, we have this theorem right here. So for quasi-system algebras, if A is a quasi-system algebra, there exists a pseudo-Hilbert space H and a isometric representation P from A to BH. So the GNS holds for quasi-system algebras. But hold on, we still not done yet. So to complete the theorem, we are going to show that morally every algebra is a star subalgebra of a quasi-system algebra, right? And as we can represent every quasi-system algebra, we can morally represent every algebra. Okay, let's head to this theorem. So first, let's define what ultra antisymmetric means. So let A be a unit of Banach star algebra. An element A with norm 1 is said to be ultra antisymmetric relative to A if for every B and C in A, we have this inequality right here. Right? This is ultra antisymmetric. But why this is useful? Why this notion is useful? This is because of the following theorem. If an algebra, unit of Banach star algebra, does not have any ultra antisymmetric elements, then it is a quasi-system algebra. So the ultra antisymmetric elements measure if the algebra is quasi-system algebra. It's a quasi-system algebra. So if A has non-ultra antisymmetric elements, it is a quasi-system algebra. And this is the final piece of the puzzle. Because if A is unit of Banach star algebra, the matrix algebra M2A has no ultra antisymmetric elements relative to M2A, right? So M2A makes the ultra antisymmetric disappear. Notice that this notion of ultra antisymmetric is relative to M2A. Relative. So we define ultra antisymmetric elements relative to A. Okay, so we have this chain of maps. Let A be a Banach star algebra, just a Banach star algebra, not unitary. We can embed in the unitization. From the unitization, we can go to M2A plus, the M2 of the unitization. Now, the M2A plus does not have ultra antisymmetric elements, thanks to this theorem. And thanks to the the first part of the GNS, we have the quasi-system algebras have a isometric representation. So we have this chain of maps right here. We go to A, to the unitization, to M to the unitization, M to, and then apply the GNS. So this way, we find an embedding of A inside the pH. So we have this final GNS theorem that states that for every Banach algebra A, such that it's known only at these values, where the normal K of K at these values, and this can be isometrically represented inside BH for some pseudo-Hilbert space H, right? This is the final result. And here we have some of the references, right? I wanna, so the main references are my thesis and my paper with Devashi with Alcides. And the main reference for this are the Anton Klausnitzer and Andreas Thom paper, right? And PhD thesis. So thank you very much. I don't know if there are any questions.
I just have like a general comment. So, I mean, I'll make this comment if there are no other questions.
So,
Okay.
are there any questions?
Yeah, just something by the way. So, you talked about like morally every algebra can be embedded, but the result seems to be at the end that I mean pretty much all of them can. At least the Banach star algebras.
Yeah.
Like I'm basically just curious as to what that was. What were the exceptions when talking about that?
Yeah.
Like yeah, but like going back to the what your comment is saying, right? It says morally and almost all. Like I'm basically just curious about what the exceptions are. Yeah.
Yeah, the exceptions are those algebras such that the norm does not attain values where the norm of K attains values, right? So for example, if K is QP, we can take A, for example, to be CP, the algebra, the completion of the algebraic closure. This so the norm of CP is bigger than the norm of QP.
But what I didn't understand was at first these ultra antisymmetric elements were a nuisance, were an obstruction, and then they were no longer an obstruction. This is what I didn't quite get.
Yeah, it's because okay, this is because of the following. A neutron symmetric element is relative to A. If we add more elements, these obstructions disappear because there are more B and C, right? We can choose more B and C such that this inequality holds, right? So if we add...
the inequality is strict.
Yeah, exactly.
Okay.
Exactly.
Yeah, so you can add more elements so that this doesn't hold for all B and C with that.
Yeah.
Okay.
When we expand the algebra, the obstructions disappear. Yeah.
And what was being a quasi? What was the definition of being a quasi system algebra?
A quasi system algebra is this definition right here. Right? The states define a pairing and a representation. Okay.
And for such algebras, you have a representation, isometric representation.
Yeah.
So the moral is you can still represent things even if they don't have this property.
Yeah. Exactly.
I see. Are there more questions?
Yeah. my general comment. So at the moment, it seems like basically any ZP algebra you pick up is going to be one of these p-adic operator algebras. And there's like while writing this paper, I was always thinking what role the involution is precisely playing. So what additional structure we've added. And it seems like the involution is not really doing anything. But this was actually made precise in this archive link I've put. So this was proved by Efimov, and yeah, it's a bit of an involved proof, but it essentially comes down to finding the fixed points of some map which is like given explicitly, and the point is that the involution or the analog of complex conjugation is just -1 in this p-adic setting. So it's not really any additional structure whatsoever. So the involution is always going to be a trivial involution. And therefore, I think like one needs to think a bit about what additional structure one needs to add to a Banach algebra to have some maybe more restrictions on what p-adic operator algebras are. So I initially thought that these Tate algebras or these things which come from rigid analytic geometry would not be examples. But once these were examples, I started to think there's basically any example we try to find. In particular, through this theorem that we have, you just take a ZP algebra that's torsion free, you can p-complete it, and then you just get a p-adic operator algebra.
But
And the star does nothing.
So in your paper, you mentioned in passing that one alternative, I mean, that the star homomorphism comes from the fact that the complex numbers are Galois with sum of 2 over the reals, and in general you want to consider. So is that the kind of thing you are still thinking?
That is exactly the thing that is answered in this paper by Efimov.
What is the...
So, yeah, I mean, I'll have
so
to
that,
get into
considering the
details.
Galois action doesn't give any new information.
Yeah, this is what gives you just -1. So this was the thing I was referring to. So he also had this, I mean, he takes the absolute Galois group of QP and kind of tries to see exactly what the analog of C to R would be in the p-adic world. And the answer he came up with was, it's just the trivial involution.
I see.
So but one needs to think about more restrictions, and it's the restriction in the C star world comes from the C star identity, and that comes from star being something non-trivial. This is not going to be the case in the p-adic world.
Okay.
Yeah. I just have another question, if it's possible.
Sorry. Yeah, please. Go ahead.
So, like, is there any, I mean, remotely decent analog of the spectral theory that typically is just talked about for stuff over the complex numbers?
Yeah, so Berkovich developed such a theory, right? But I'm not very familiar with these. Do you know this?
Yeah, so this is developed over any Banach ring, and you will find this in Berkovich's book.
There is a Berkovich spectrum, right?
Yeah.
Sorry, can you please type the name in the chat so I can look it
up?
Yeah. I've never heard of it.
Do you know how to spell
Berkovich? Oh, yeah.
Spectrum. The guy's name is...
Okay.
Yeah, and when A is a system algebra, the Berkovich spectrum coincides with the usual spectrum of the system algebra, right?
Yeah, the Gelfand spectrum.
I see. Okay, thank you.
Okay, so if there are no more questions, I'll stop the recording now.